Looking at household appliances, you'll find an inspection plate or a rating plate on most of them that will have some basic information. The information usually consists of telling you the voltage and the amperage. The 60 hertz just means it's alternating current. It'll always be 120 volts if it plugs into the wall in Canada, and it'll give you the current, or it will state the wattage all by itself. So this is telling you how many joules a second. This is telling you there are 10 coulombs of electrons per second, 10 cups per second, and this is telling you how many calories those things have in that sense, how many joules per cup. So you might see 100 watts, or instead you might see 5 amps at 120 VAC, which is volts alternating current. So they might just say V or VAC VDC. Doesn't matter. They might even say 120 volts and a wiggle indicating wiggling. Either way, we can say 5 cups per second of electrons, 120 joules per cup. You multiply the two together to get your power. So the power in this case would be 600 watts. Okay, there's our 120 volt wiggle as the computer hangs up. The nameplates that come on things will often have a lot of information on them. All we're really after is the volts and amps. They don't state watts, just multiply these two and you've got your wattage. Typical devices report power. They do not report energy. The energy you're going to use depends on how long you leave it on. So $5 an hour for 3 hours is $15 of money. We don't tell you how much we're going to pay you. We tell you the rate we're going to pay you, and then it depends after that. So if you had 5 joules a second for 3 seconds, that's 15 joules in total. Okay? Now the 5 joules per second is the same thing as 5 watts. What happens if you had 3,000 watts running for 4 hours? Then the 3,000 watts, you turn your 4 hours into seconds, and you get 43 million joules. Because this watt is a joule per second times seconds. Now this is a very large number. In everyday life, we don't use meters per second, we use kilometers per hour. So the same thing is going to happen to energy. We're going to bundle the energy into bigger units. Given the formula for energy, there's our rate of flow, joules per second. That is how long it is on. You combine the two and you get your total energy. So a 3,000 watt light bulb turned on for 4 hours would be 3,000 watts times 14,400 seconds. But instead, let's bundle it. We'll turn the watts into kilowatts, and we won't bother with the conversion to seconds. We will simply leave it in hours, and then we get 12 kilowatt hours, which you read as 12,000 joules per second of power running for 1 hour. It is a total. It's just bundled conveniently. Now, what if you want to unbundle it? It's dead easy. 12,000 times 3,600 seconds. The conversion is quite easy. In fact, I wouldn't dignify it with the conversion. You're just swapping out K for what it means and H for what it means. You leave a 100 watt light bulb on in your room for 8 hours. What's the total energy it used? Well, there's 2 ways of calculating this. The scientific method and what I call industrial or household. The scientific method would simply say you're going to multiply the power times time. And this 100 watts again is hiding joules per second. And this becomes dead easy. Oh, I'm using up 100 joules per second for 8 hours, but I got to do 8 hours in seconds. So I'll just multiply it by how many seconds in an hour. There we go. I'm all set to go. I repeated the line again for some stupid reason. I've repeated this twice, and I've edited this 5 or 6 times, and I've yet to notice I did the same thing twice. Anyway, when it's all done, I suppose I meant to leave this as a watt, just to show you. When it's all done, we get about 29,000 joules, 29 kilojoules of energy, which means nothing to you because you're not that used to joules. It's not very much. In kilowatt hours, it's a little bit different. You do P times T, and you do not touch the hours, but the watts have to be bundled into kilowatts. Now, 100 meters is the same as 0.1 kilometers. 100 grams is a tenth of a kilogram. So 100 watts is only 0.1 kilowatts times 8 hours. We get 0.8 kilowatt hours. That's like saying, oh, I get it. That's like turning on a light that's 0.8 kilowatts. An 800 watt light bulb running for 1 hour. That's the total. They are completely equivalent. If you change this to 1,000 and you change this to 3,600, I guarantee you will get this number. If you take this number and divide it by 1,000 and you divide it by 3,600, you will get that number. They're the same thing. So what can we do with kilowatt hours? Because you will see it reported outside the classroom like this most of the time. 2 possibilities. Convert it to joules. 10 kilowatt hours, the K just tacks on 3 zeros. That's all it does. And the hour switches to 3,600 seconds. I bundle them nicely, and I get this, and something stomping on it. The slide moved over a bit. I hate this. Looks good in practice, not in reality. And this lost the multiplying sign. Anyway, we get 36 million watts times seconds. And that's what's got stomped out here. Watts times seconds is supposed to be here, but it's got smushed. So what do we do with a watt times a second? Well, think about it. If a watt is a joule per second, then a joule per second times seconds is a joule. So when it goes round the clock like this 36 million watt seconds is the same thing as 36 joules. And then the mega takes over for that. That would be your basic conversion. The other possibility is turn it to price tag. You look up what electricity costs, and in Ontario, that's your peak cost. Multiply it out, and you get leaving that 10,000 watts on at 10 kilowatt hours only costs you $1.34. That would be the equivalent of leaving 5 hair dryers on full for an hour to get this number. Okay? And it only costs you $1.34. As you heard from the bell, I have to pause.